This lecture is on integer linear programming. It's one of two lectures. Why do we want to use integer linear programming? Originally in this class we have seen that we could solve problems by rounding up or down the final answers of the optimal solution, thus avoiding to say that this particular decision variable or the other is integer or not. So if you are, let's say, producing in these production problems that we have seen throughout the class, if you are producing chairs and tables in a certain factory and the optimal results ended up being x1 equal 17.6 tables, then you would basically round up or down saying it's 17 or it's 19 tables to produce. This fraction of a table or a chair wouldn't make a big difference to the overall profit, or to the overall problem. But sometimes it's not easy or it's not useful to round up or down in situations like, let's say, we're modeling a problem where we're trying to decide whether to build a power plant or not in a certain location. So getting a value of 0.6, rounding up or down, would cost you 20-30 billion dollars maybe in cost, whether you decided to round up or round down to 0 or to 1. So some problems really cannot be treated like a simple production problem where a fraction of a production of a unit is not very important considering the overall production capacity, versus when you were talking about these substantial investments in a power plant or in a certain factory to build, and which requires hundreds of millions of dollars of investment. So rounding up and down becomes a problematic in this situation, and we need to figure out a way to solve the problem and where the results end up being integer actually, and not by rounding them up or down, because it will give us a wrong answer, or at least not an optimal solution. So this chapter is going to be about that, dealing or treating decision variables that are binary or that they are integers, whether they're 0, 1 being binary, nothing in between, or whether they're integers and not fractions. And we have to force the solution to the optimal solution or the final solution to be a whole number. Okay. So here's the outline of this lecture. And as I said, I'm going to talk a little bit about situations where we need to formulate the problem as an integer program, a linear integer program, ILP, and we cannot just formulate it as a simple linear program or as a regular linear program where the answers could be fractions. We look at some of these examples and formulate them. And then in the second part of this lecture, a very important topic regarding formulating logical constraints. So far we have seen in this course that most of these constraints that we use or formulate in the problems are of the type AND constraints. That means we need to satisfy all the constraints at once. Sometimes maybe we need to satisfy a subset of these constraints, or either or that constraint, or if then constraints. All these types of logical constraints we haven't looked into, and they are very important sometimes in formulating a problem. So facing such a situation, how do we handle these? How do we formulate logical constraints in mathematical terms to use them in our problem formulation? Then I will talk about a few types of important classes of linear integer programs. Time permitting, we'll see. Location allocation problems, where to locate. And set covering problems, where also to locate, to cover a certain geographical area, let's say, building a mall to serve certain counties or locations. And this is called set covering problem, or building a fire station also for a few to cover a few cities, and where is the best location if you want to minimize the number of fire stations to build. And finally, a very famous problem also, which has various applications in various areas, traveling salesman problem, TSP. And we'll also look at how is this problem formulated as a linear integer program. The second lecture on integer programming, I will cover how do we solve linear integer programs using branch and bound methods. Okay, but this is for second part of this lecture. Okay, linear integer programs, LIP, and can be formulated just like a regular linear program. The three components are objective function. It's a linear combination of these various decision variables, the vector xn, x1, x2 through xn of decision variables, linear combinations of these. The ci's are known deterministic values, and this is a linear combination of these decision variables, just exactly like the regular linear program. And then we have a bunch of constraints, so we have an objective function and then a list of constraints subject to a bunch of constraints. There are m of these constraints, and they're also the same, linear combinations of these same decision variables. The aij's are known deterministically, and then the only difference, as you can see here, is xj or xi. I was saying it. Okay, xj is j from 1 to n is um, integer. Take only integer values. So it looks exactly the same, except for the fact that instead of saying xj larger than or equal to 0, the non-negativity constraint that we used to use, now no, we have we have the non-negativity constraint here and an upper bound there, but an added extra constraint here saying that xj is binary, sometimes 0 or 1, nothing in between, or an integer 1, 2, 3, 4, and nothing in between. Um, there are various types of integer programming models. A mixed integer program, which we call MIP, MIP, is that some of the decision variables are continuous and some are integers, and thus we call that a mixed integer program. Um, if all decision variables are integer, we call this a pure integer program or just an integer program. Special case of integer programming, when the decision variables can only take binary values, 0 or 1, then we call this a binary integer program, or BIP. Okay. Okay. So why study integer programming, or why have a separate discussion for it if it's just a linear program? As I mentioned earlier in the opening slide, that sometimes the fractional or continuous solutions that we assume to be okay are not valid anymore. And as I gave you a simple production problem where you're producing tens of thousands of tables and chairs, and then if your final answer came out to be 10,000.17 chair, that's fine, just do 10,000 chairs. That you don't have to do an extra chair. So you round down or up, doesn't matter really. Um, the other thing I also mentioned briefly is, the use of logical constraints. Integer programs are important and necessary when we use logical constraints in our formulation. Things like if-then statements or if-then constraints. If this constraint, if the value of x is this and that, then I want this constraint to be active or not active, and maybe something like this. Maybe I want a subset of these constraints to be active and not the other subset. So kind of like either or constraints, because so far we assume all the constraints that we have in our formulation are and constraints so far. So if you have a list of constraints, you need to satisfy all these constraints. What if I want to satisfy only a subset of these constraints? Then I need to use some logical constraints which involve um, integer variables in the formulation. Um, so another thing that I want you to remember also, that sensitivity analysis is not available when we do integer programs. Okay, so it's unlike linear programs where you can do sensitivity on them. With integer programs, this property, we lose that property, so we cannot do sensitivity. And in order to figure out the effect of a change on the problem, we may have to resolve the problem uh, from scratch altogether. Just plug another number and solve it again. In general, ILP problems are much more difficult to solve than linear programs, because we lose all the properties that make linear programs easy, which is the continuous property. So in integer linear programs, we don't have this continuous. So we have a solution at point, let's say 0, 1. if x1 is 0 and x2 is 1, but you have no solution between 0, 1 and 0, 2, another point. So you lose this continuity property that makes, as I said, LPs easier to handle or solve. So it becomes more difficult to solve integer linear programs than linear programs. So if you can avoid using them, actually, it's better in general. In reality, in real life, in practice, if you can avoid using integers for decision variables, it's better. So the lesser the better. So if you have just few, it's better than having all of them being integers, just a few decision variables in your formulation. Okay, so let's take a look at a simple problem that requires integer formulation. Um, Here we have an example of a site selection problem, four potential sites, uh, four potential sites, 1, 2, 3, 4 to build, and three potential designs to choose from, A, B, and C. Okay, so you can build on site one using either one of these three designs, or you don't have to build actually. It's like you have, a fourth design here saying don't build at all, A, B, or C, or don't build in each one of these different four sites. Um, and you have here an example saying option, if you build in site one using design A, the net income is $6 million, and the investment required to do that is 13. So it's like, okay, so so you get back 6 return on investment of 13. And if you do that in the same in a different location using the same design A in location 2, then it's basically you invest 20 million and you get back 7 million, and so on. So I'm not sure if it doesn't show in this slide whether you must build using one of these designs, or is an option not to build at all. Now we'll figure that out maybe in the next slide. But for now it's not clear that you don't have to build on a specific site, or the other option is you must build one using one of these designs. So the budget of the company is 100 million, and the objective is to maximize total income without exceeding the budget. Okay, so basically, yes, we probably have we don't have we have a choice not to build actually in this case. Okay, so we have set I that has or index I that has the different designs, design A, B, C, and the set J or index J that has the four different locations, 1, 2, 3, 4. And then the first thing we do, just like any other regular linear program or any regular programming problem, that we need to define our decision variable. In this case, the decision variables are Yij equal 1 or 0 binary decision variable, either to build or not to build. If Yij is 1, that means build in location J using design I. Okay, so if design I is used at site J, that's fine. Same thing, and 0 otherwise. Okay, so, and the objective function is I want to maximize the return, and then PIJs are the returns on investment that were shown in the previous slide in that table, and it says double summation over i's and over j's, so over all the locations using all the designs PIJ, YIJ, and just note here that it doesn't protect, of course, the objective function of building multiple designs on the same sites, because it doesn't know. But so you'll have y1 or ya1 plus yb1 plus yc1, all of these with part of this objective function, and then we let some of the constraints decide that these y only one of these y1 fixing location j to 1, yi1 equal to maximum 1, because you want it to be less than or equal to 1. Otherwise, you would be building you will build building on the same site using different designs, and that's not allowed. But anyway, we protect against this in the constraints. But going back to the objective function, then this is fine. You want to maximize the profit coming from the different designs, and that's simple enough. And then now we have subject to the investments, and also present in the previous table, AIJ, how much to invest in the different designs, and that should be less than or equal the 100 million. Um, Beautiful. And then we get the YIJ is being binary, either 0 or 1. No other alternative. Now the question is this complete? Well, it's incomplete because why? Because I just mentioned this already, because I didn't protect against building multiple designs on the same site. Using multiple designs on the same site, I have to protect that. And I also have to protect the other constraint that I need to use also is to protect basically building more than, let's say, one more building more than one building more than one building or design use on the same site also. So we're going to see this in the next slide. Here saying that it should be at most one. You're summing over j being the different locations. So basically, so I'll take j equal to 1, and then I have the summation of y I1 over I. So the different designs, that means it's YA1 plus YA2 plus sorry. It is YA1 plus YB1 plus YC1 should be at most 1. That means it could be 0 also, because you don't have to build at all using any or none of these designs at all. Don't build or build. And if you do build, you just can use one design and shouldn't be two or anything else. So that's the first type of constraint. Okay. And okay, do I need any other constraint type? I don't think so. Now here's just a special constraint saying that site 2 must have a building. So that means, they force you to build on site 2 for whatever reason, that you need to have a building on site 2. So look at this, the summation over I. It doesn't matter which design you use. It could be A, B, or C, but J2 must have a equal to 1. So one of these must be used. So here they're forcing you to build on site 2 regardless of the design you select. Another very famous problem in financial engineering is capital budgeting problem. Capital budgeting problem, also known as a multidimensional knapsack problem. Remember the knapsack that we uh, looked at in the previous chapter in the dynamic programming? This is a multidimensional knapsack. That means you have more than one knapsack actually. Um, okay, or you can think about it actually. You're having a single knapsack but with more dimensions. It's weight, volume, and I don't know what else the other dimension that is. But anyway, it's a very popular application to integer programming is this capital budgeting problem that belongs to a multi-dimensional knapsack problems, set of problems. Um, but the idea is simple. You need to select a subset of projects from a number of projects, a set of projects that are available to be worked on, but you need to select a few of these, a subset of these to work on in order to obviously maximize the return on investment, but also subject to some constraints regarding, basically availability of resources. Here's a nice example from NASA, and they have about 14 different projects that they can work on, and these are the various investments during a period. So let's just imagine this 2000 2004 is a future period in time, um, and that means they want to invest here $6 million, let's say, and the value here is of doing this project is 200 units of value. And these are some of the constraints we're going to see here. For example, 5, that means you cannot do project 4 with project 5, not with. For some reason, they don't want to do them together because maybe they are too similar or they're conflicting or whatever that is. But and then depends on 3, and that's O. So you cannot do 4 unless you do 3. So that depends on. So just the opposite concepts here. You cannot do it with. So they are exhaustive, collectively exhaustive. 4 and 5 can be simultaneously worked on or selected for this portfolio of these projects, while if you select 4, you must select 3, or 3 must be selected as a predecessor for 4. And those are similar things that you can look at. The budget available for each year or each period actually of future periods, and you have period 1, period 2, period 3, period 4, period 5. So we have 5 periods, and we have a budget of 10 million, 12 million, 14, 14, and 14 for each one of these 5 periods. Okay, so the question is, how do I select which projects to select, considering the resource availability or limitations, and also some of these dependency structures that I have. And obviously, you can either work on the project or you don't at all selected. You can have partially work on the project, and that's why it's an integer problem, because either you select the project and work on it, or you don't. So there's no, I want to work on it only 40% or fraction of the time or fraction of the budget. So how do we formulate it? Very simple, as I said, these problems are simply formulated. Um we have the decision variable xj, either 1 or 0. It's 1 if you select mission or project J is selected, and those turn out to be missions for NASA, but we can look at them as projects, doesn't matter, and then 0 otherwise. The budget constraint is straightforward. So we add all the column in the previous table, and the various investments, and this requires 6 million for if you work in project 1 in period 1, 2 million if you work on project 2 in period 1, 3 million if you work on project 3 in period 1, and so on. All of these will add up to less than $10 million that is available budget for year 1. So there's a bunch of these constraints, and these will take care for the actually for 5 periods, actually not years. They should be period 1 through period 5 and not year 1 through year 5, because each period is a multi-year actually, I think. Okay, so now the other constraints that are haven't addressed, these have to do with mutually exclusive choices. That means, if you select, remember I said, or I mentioned that if project 4 or mission 4 was selected, you cannot select mission 5, and that's basically mutually exclusive. That means x4 plus x5 at most is 1. One of them is selected. If 4 is selected, then 5 cannot be selected because the sum is less than 1. Or if 5 is selected, 4 cannot be selected, or both don't have to be selected at all, and then basically the sum will be 0, so that's still fine. Okay, and that's a very simple way of representing mutually exclusive choices or selections in these kinds of problems for the capital budgeting problem. And dependencies are a little bit trickier, but still easy. And it's saying here that x2 it depends on 11, I believe. That means, so basically if you take x11 minus x2 less than or equal to 0, so that means that project 11 depends on project 2. You cannot do 11 unless you have done 2, and that's why, so x11 minus x2 should be less than or equal to 0. So x2, if x11 is 1, then x2 must be 1. Then becomes 1 minus 1 is less than or equal to 0, which is 0 basically, because there is no negative as allowed. And then, if x2 is 0, x1 minus, actually x negative is allowed, because if you don't select x11 but you do select x2, so x11 minus x2 would be negative, which is fine, it's allowed. Okay, because you can select x2 without selecting x11, so then becomes 0 minus 1 is minus 1. But you cannot select x11 without selecting x2, so that means you will never have x11 is 1 minus x2 is 0. So that means 1 minus 0 is 1, and this is not less than 0, so it's not allowed. And that's how it works. Very simple, but logical relationship between those two projects to implement or to enforce this dependency relationship. Okay, to formalize this, we have these logical constraints. Either or we start with either or constraints, and basically we have two constraints: f1 as a function of those n decision variables, and f2 as another function of the same decision variables, and the right hand side is v1 and v2 for those two constraints. However, this time we don't want both of them to be satisfied, just like what we used to do. So I want either this or that constraint to be effective or to be not violated. A very simple trick is to add a binary variable to one of them and multiply the other by 1 minus that. So basically, uh, m is a very large number, and y is a binary variable, which is either 0 or 1. And I multiply one of the constraints by m, and I multiply the other constraint by m into 1 minus y. So that means when y is 0, this part of the first constraint disappears, and then the constraint becomes f1 less than b1, while the second constraint, because y is 0, it becomes plus m, and so it's m is a very large number because 1 minus y, we said 0, so we have m times 1 is m, and m is a very large number times b2 or plus b2, it doesn't matter, so m is very large, so it's less than m. M is kind of like infinity, and we're saying that f2 is less than infinity. Well, it doesn't have any meaning, and that's why we call it redundant in this case. It doesn't matter. This constraint doesn't exist, the second one. So obviously the other way around, if y is 1, then this becomes redundant. The first constraint becomes redundant, and the second constraint becomes in effect. And that's how we deal with either or constraints in a particular formulation if you need to use it. So other logical constraints here, as an example actually of this if then, we're saying that we multiplied, yes, either x is less than 0. Yeah, this is the logical constraint. Either x is less than 0 or x is larger than 100, so either or. I don't want both to be satisfied. I want either or. So this is two different constraints. I multiply the first constraint by my, so it's 0 plus my, and then here it's 100, but I got the 100 to the other side here, and then we got m into 1 minus y, and y being binary. Okay, and since those are the numbers, we're saying in implementation, for implementation purposes, if you are implementing this on a computer, then m would be considered 200 is a good number to consider, or 1,000 is fine too. It works well with this problem because the units of this problem is the maximum number is 100 anyway. Okay, but just assume that m is a very large number relative to the numbers used in the problem. Okay, out of n constraints, another type of another type of logical constraint. In the previous slide, we saw either or, so either this constraint or that constraint. Here, no, here is subset. It's kind of like a subset either or. So we have, I want a subset of these constraints to be in effect. So what I do, I multiply all these constraints. There are n of these constraints from the right hand side b1 to bn, so I multiply by, I come up with n binary decision variables. Y1 is 0 1, y2 is 0 1, and so on. So I make up n binary decision variables, y1 through yn. I multiply all the constraints by m into 1 minus uh, yi, and then I add this constraint that the summation of the yi's should be at most, or should be equal, not at most, should be exactly k. So because I want k out of n constraints, so there are a total of n of such functions or constraints, and I want only a subset k out of these to be in effect, to be effective. So I add this constraint also with the rest, and thus I will have a formulation for this particular logical scenario. If then constraints, another very popular application of integer programming is the use of if then constraints. And um, and the way we handle this, or if we formulate this if then constraint, is as a we start from the either or formulation, and then we arrive at a solution for this if then. And the way we do it is as follows. It says if a is larger than 0, and a is a logical statement that can be formulated as a functional form. So if a larger than 0, then b is larger than 0. So remember, that means only if a larger than 0, then b must be larger than 0. So uh, b could be less than 0, and a can be anything. It doesn't matter. Okay? So that's really how we understand. So I divided the statement, the logical statement, into two parts. If a is larger than 0, then b is larger than 0. So a and larger than 0 and b larger than 0 happen together. Either this or that other statement that a is less than 0, then there's no condition on b. B could be larger than or less than, it does not matter. So two statements, then this becomes either or. Instead of if then, this becomes either or, either this statement or that statement. Okay? So, and then the rest is just manipulation here, saying that, uh, you know, a is larger than 0, that's still a is larger than 0, and b is larger than 0, a is less than 0. This is nothing. And then we have, okay, so we multiply, and we said either or this becomes, so multiply one side of the either or statement by my and the other one by m into 1 minus y, and thus we have the two statements, 0 less than a multiplied by n by m, and 0 less than b multiplied by m. So this is the one side of the logical statement, while the other flip side of the logical statement is multiplied by m into 1 minus y, and thus we have this either or sorry, thus we have this if then statement originally here is converted into either or statement that becomes similar to what we've seen in the previous slide for either or formulation. Okay, here's an example of this if then scenario, and let's assume that xi means that the start of job I, and that's a decision variable, while pi is the processing time of job I. So this is a scheduling problem, and then here's the logical statement. If job I precedes job J, that means it happens before job J, so I is before J. If that happens, if I is before J, then K must be before M. So if I is before J, that means, I, the start time of job I is Xi, plus the processing time of job I, Pi, must be the whole total thing. So that's the finish time, actually. Xi plus Pi is the finish time of job I, must be less than the start time of the successor activity Xj in this case. So, and that's this logical statement. So, but if this happens, this must happen. That means also K must precede M. So xk plus pk must be less than or equal to m. So how do we deal with this logical scenario or statement? Is by basically multiplying this by my and this by 1 minus my, or the other way around. Actually, you can multiply, it doesn't matter which one you multiply by my, and which one you multiply by m into 1 minus y. In this case, they use w anyway, not y, so still w is a binary variable, 0 or 1, and then one statement is multiplied by m, the other statement is multiplied by uh, 1 minus w, and the other statement is multiplied by w. Okay, so here's another example also, quickly, same thing, m and multiplied by m into 1 minus y. Difference here is that we took the sum because they're all zeros. Okay, let's look at a comprehensive example that has all these various logical statements or constraints and try to take advantage of them to formulate this problem. Stockco is considering 6 investments. The cash required from each investment, as well as the net present value of the investment, is given in the next slide. The cash available for investment is $14,000. Wants to Stockco wants to maximize its net present value. So what's the optimal strategy? That means, again, this is a capital budgeting problem, and what should they select? What subset of these projects need to be invested in? What's the portfolio that will maximize their returns? Here's the data. We have an investment budget of $14,000. And then we have the various investments. You have 6 different investments, and the cash required for each is listed here. For example, for investment 1 or project 1, we need $5 million or $5,000, sorry, to be invested. Okay. Net present value added is $16,000. That's how much you make. Okay. So similarly, the other 6 investments. So what are the decision variables? That's the first thing you want to figure out. And obviously, it's a binary decision variable, xi, where I equal 1 if you invest in project or investment 1 and 0 otherwise. And you have 6 of these different investments, I from 1 to 6. Objective function and constraints. What's the objective function? Is to maximize the return. So we have 16x1 plus 22x2 and so on. These are the various return on investments for the various projects or investments. Very straightforward objective function, and then now we come to the constraints. Exactly 3 stocks are selected, so we need to exactly select 3 stocks. How do we do that? If stock 2 is selected, then so is stock 1, so that means dependency relationship. If stock 1 is selected, then stock 3 is not selected. Okay, so that's mutual exclusion, and either stock 4 is selected or stock 5 is selected, and those either or button. So stock 3 is selected, the maximum, so x1 through plus x2 plus x4 until x6, that makes it equal exactly to 3. If stock 2 is selected, then so is stock 1. That means this is dependency relationship. Remember then, it's x1 depends on x2. Okay, so you can write it this way, or x1 minus x2 is larger than or equal to 0. So basically, x1 depends on x2. Okay. Okay. If stock 2 is selected, then so is stock 1. If stock 1 is selected, then stock 3 is not selected. So those, you want to add them up, should be less than, the most is 1. So both do not have to be selected at all, but one of them at most will be selected. And finally, we have either or, so one must be selected, either this or that, but not both, obviously. Here's another example that I'm gonna skip, but take a look at it from the PowerPoint slides that I posted on Moodle anyway. So, but it's the same, more of the same, just give you a chance to go over these formulations for integer programs and exercise your ability to formulate logical constraints. So I'm going to skip these over, but take a look at them and try to answer them. These slides are posted on Moodle already anyway, but there's nothing new on these slides. So here's the example. You know, there are 7 different product lines with various investment amount and requirement. So they need you to select which lines to select in order to maximize the return, and similar constraints that need to be formulated using some of these logical constraints.